and you're going to search in the database, and you're going to use the index to find potential matches. So the blocking there was not doing with real blocking, but you use the index to sort of block these kind of things. Now, these things have some problems because, for instance, those are 5 records somewhere in a database. And you see that the first 2 can be matched because they have something similar. The other 3 can also be matched, but the record in the middle is not going to be matched because it's my wife. So you're only going to get these 2 matches. And you see that there clearly is some sort of path going through that data that maybe you can link A and E also together, because there is a very strong path between those data points. So you see the path. So we saw paths going on that data. We saw these blocking kind of issues. So we started thinking, okay, path traversals, graph locality, locality of data. These are typically things that maybe graphs are good for. So we decided, okay, maybe we turn the problem around, and we're not going to do that indexed stuff anymore. Or we're going to make it better than the indexed stuff, because we want to find, through a path of data that's left behind, digital trail, we want to make comparisons between these things that maybe in a pairwise combination you're not going to see. So like I said, we're going to use the graph locality, and we're going to use the pointer hopping, and that led us to having a sort of implementation of a graph algorithm. So the blocking thing really looks like detecting of certain communities, and the thing that I contributed was the strongly connected component algorithm, and that's based upon some guy in the 70s who devised the algorithm, how to you can check it. So it's the Tarragon connected component algorithm is what I used to implement it. And the thing is that I've implemented the general algorithm, but I also extended it with more domain knowledge so that we can do a lot more stuff with the algorithm, because in my graph everything is connected, because there's a connection between a street, and a street has a municipality and has a country. So there is a path from every people to every other people. So if we start community data connection like this, it's not going to work. But then you can decide, okay, so that's what I mean by everything is connected, because there is a tree of geolocation. Yes, so that's the demo. Click it here. Wait. It works. Oh, wait, that's another presentation. This is the one. Okay. So because we used a geolocation in our graph database, everything is connected through perhaps a country, and we also use time in our database of when certain things happened, and then we use the time tree for that. But having a time tree and a geolocation tree in the graph also made us possible to make comparisons between more remote geolocations, or maybe make comparisons in the time. So what I mean, so if a record comes in, and I can make a comparison between every record that is coming in, for instance, for one day. We can make all these combinations there. Or maybe I can have I have a record, somebody living at number 12 on a street, but I have also another record where there's no number in it. I can make the comparisons and say, okay, we are going to only make connected components out of streets. We're not going to take in the municipality. So what we do in the algorithm is we cut loose certain relationships that are there, but we're not going to take them into account in the algorithm that is going to make the comparisons between those kind of things. So that makes this algorithm that's research extendable. So you can say, okay, we're only going to do the 12, only when the numbers match, or we're going to do it when the street matches, we're going to do it in time and things like that, and start creating these islands, but you decide how these islands are created. So for instance, you can only, when you detect, you can only, this rule is going to go into connected components where the number is correct also, so it's not going to detect the matchings there. And the nice thing about when you structure your data as a graph is also that you're starting to detect that a lot of from these clusters, they are households in Belgium. So, and also what we discovered when we did some testings for other companies that gave us data to start detecting duplicates is that for some certain cases, detecting these duplicates was very hard. And why it was hard is because the people that were at the counter were not describing them as persons, but was describing them as households. For instance, it was a gaming shop, and children were not allowed to have a membership card, so what the parents did, they created a card for their kids. But then they used maybe the email of the father, the name of the mother, and things like that. If they wanted to do a pickup, they didn't use their own phone number, but they used the phone number of the children or something like that. And you started to see that all these records were mixed in a certain way that we were not able to detect a lot of people, really unique people in those things. And then we started to see in the data and discover it. And then we said to the client, but do you sure that you want to target people, or do you want to target households? Because households, if you're a gaming shop, maybe that's more a thing that you want to target in the past. And that's something that we found when we were searching in the data. And it was very easy for us to target households because apparently these connected components are more or less the households you want to target. So now that's for my theoretical approach, and I'm going to demonstrate it, how it works. So the thing is that we created some services around Neo4j. I started this service right now. There's currently nothing in the database. Going to add some records. We created some REST services around it. So this one is going to insert 5 records or 4 records in there. The thing is, I always need to change the port number because it is set randomly. So we retrieve the connected component IDs and the node IDs from that. So now if we search for those people, it's a bit bigger. You see that there is a path. This is one of the connected components that is in there. And this is what we're going to make the similarity between all these kind of things. So then we need to run the algorithm. Run it again. Right. It didn't. Wait, I have to check the name of the job again. That's better. Now you see that these components are all linked together. And the link that specifies them also says why they are linked in between. So you see that this one is linked because last name, first name, phonetic, and gender and graph are matching. So what does graph mean? It means that he has gotten to that other record through a graph. So through my wife, he found a similarity between those two records. So now, what it also made possible is if we use these kind of traversals to make pairwise comparisons between records, is that okay, I missed something. Is that you can have several customers, data sets together, and you can traverse even the customer's, another customer's data set and get back into your data set. So maybe the record of my wife is not in my data set, but it's in another person's data set. So the idea, so first we wanted to create a product that can be set at some party and they can do it with their own data. In the end, it was the idea to have a sort of central system where only data comes in, but it can be encrypted and hashed, for instance, so that it's anonymous for us, but we have all these kind of nodes together, and we can have these paths going to other data, and we can say to you, okay, you have provided us those two records, but we can show that we have other data, that these two records, they have a graph path between them, and they are probably the same person there, because we have another node. So to demonstrate this, I have to delete everything. So it's empty now. So for instance, I'm going to insert 3 records from customer A. Wait, again, the port number. So you see in this data set, there are distinctly 2 connected components. There is no link between them. So if you start pairwise comparing them, you're not going to find anything. So if we run this job here, it's not going to make a distinction, but if we insert the extra record, there's going to be this path between them, meaning that extra record of that other customer. And if you then run the linking algorithm again, it's going to link them together. So that was where we stopped because funding stopped the thing, because we couldn't sell it to customers. But I'm still a believer that this kind of solution has its purpose and that it has an added value instead of doing this index-based comparison, all these paths. And because it's extendable, like using the art tree, using a time tree and things like that. And that was my first introduction to the graph algorithm. So hopefully this makes some sense to you guys. So if you have any questions about it, just shoot.
Is that an algorithm in enabled or?
So the thing is that I have created the algorithm, but the algorithm has a node and a relationship. Most of these algorithms, they function on just one type of relationship or one type of node. The thing is, for this, I wanted to have all certain relationships not into account. So I created, and on top of that, I created another algorithm with more specific information of that. So I have created an old stored procedure based upon the other stored procedure that you can say, okay, I don't want this relationship, I want that relationship, and things like that. So that's more in there. Plus, during my traversal, I also count stuff, other stuff to do specific statistics on later, because if you want to do statistics later, going back through all your graph is kind of slow. So that's why it optimized. So I took a general algorithm and put some domain logic in there. So that's the store procedure created. This one is now available in the new graph algorithms, so the connected component, but the connected component is not available with my specific thing in it. So with the time tree, with all these things that you can say, okay, I want to have it on street and things like that. It's more specific for my stored procedure. But that stored procedure can also be made available. That's not a... Yeah, but the problem is for the probability. Yeah, so the rules, you can provide also rules in that system saying, okay, for that customer, he wants to have these kind of combinations, and if for instance that is important. So when you run the algorithm, you have to have the specificity of the rules. So when it does a pairwise combination, not everything is going to get a link out of it. So it's configurable, but for the customer, it was really important that when two people get linked together, that they can know why it's linked together. So because you have all these duplications that are also probabilistic, saying, okay, yeah, there's a distance function, and if it's more than a threshold, there are people put together. But for this customer, it was very important that when two people were made together, that they knew why it was made together, because otherwise, if you do the duplication in some certain cases and it's wrong, you need to prove why it was wrong. So that's also in that system. Now, this is also something that this is only a little subgraph. If I open the complete graph, it with all these timings and things in it, it's a much more complex thing. So. Mm-hmm. So, so yeah. So what we've done, I've written a Scala microservice around it, and it has a Rust interface, and it just translates it in a stream and puts it in Cypher in there. So that's something that we implement. We use it to do also really because we had to do 1 million inserts of records in that system, and the pairwise combination in the previous system took 8 hours to do all these combinations on the index-based, but index-based without the graph traversals, so just really, okay, matching, not going through. And we had to create a system, and for us it took 1 hour to insert 1 million records and do all these matches between all these records and things like that. So that was highly optimized for that. If you start doing these kind of things, there are really special cases you have to check. I don't know if in the newest Neo4j database, but I didn't go into details of it, but when I used a number that was going up and it was indexed, it was slowing down really the ingestion, because probably he had to recalculate the index all the time because it was a number or something like that. If you made it a string, the upgoing number, it was fast as hell. So these are really strange things that you noticed when you are working. I don't know if it's because the whole index is now changed in the new version, don't know what was happening there. So no, no, I need to index this is a system. That's not. That's not.
Yeah, it's not completely clear. So you have, in the end, you have a path between everything. So people building at the same.
Yeah. So by in my algorithm, yeah.
You can always.
But in my algorithm, I have to say, okay, but don't traverse street. So there is. I made a virtual graph of it before I run the algorithm. So some relationships are not to be go over with. The thing is that the advantage also of this graph kind of matching is that you can really detect these kind of big clusters of maybe people are doing fraud kind of things. People that are creating digital identities and the fake identities, you can detect them because you have really big components. And in my streaming, when I calculate the components, I also have this timer saying, okay, this is a component that really takes a long time to think. You have to go and search for what is going on with that identity. The thing is that, for instance, hospitals, no, not hospitals, but for elderly people, really big buildings, they tend to be really slow because it's one address or something like that. So they start comparing all these things. But you detect that, so no. Further questions? Okay.
Does the sound work? No? Connected? It has to do with the adapter. I can take it out and back in. He's seeing it. Okay. Let's see if it keeps working. My name is Ignaz, and like Tom, work for the same company, Vector Consulting. And we have been doing some graph work for quite a long time already, since 2012, I think, or something like that, 13. At least before Rick came in the picture. I'm going to tell you something about a small project that we did about building a knowledge graph. So I'm going to explain you a little bit about what a knowledge graph is or can be, and how you can create one yourself fairly easily using some machine learning techniques as well to populate the graph. The term knowledge graph was actually first put forth by Google in 2012. It's the way their search engine works. If you are searching for a movie, for example, you will not only get the search results for the movie itself, but you will also get search results for where the movie is playing in your neighborhood and what the times are and so on, and who is the main player in the movie. All these kind of things are connected entities that form a graph, and Google has used that in its search engine, and that's why you see when you search something several different categories of search results. But a knowledge graph is much more general actually than what you can do in only searching. Here's an example. On the left we have just a simple string. We can make there an entity. We can define it as an entity. And that entity has a lot of relationships with other entities, whatever they are. And these relationships, you can name them. For example, Leonardo da Vinci is born in, then you have a city, for example. He has siblings, these are other people, and so on. So you can see that anything, any entity you can add to the graph, and you can connect it to any of the other entities. You name them, and that's the basis of a knowledge graph. So any types of entities, named entities, you can put forth, and the relationships. There is no clear definition of a knowledge graph. If you look it up in Wikipedia, it's a terribly complex definition about ontologies and so on. I found one sentence that I like that could describe a knowledge graph, and that simply is: a knowledge graph acquires and integrates information into an ontology and applies a reasoner to derive new knowledge from it. The key elements is that it is a graph. Everything is connected to each other. So that's the definition of a graph. It's also semantic. It's a self-describing thing. So the relationships, the names of the relationships, they basically describe what the relationship means. And that's why it is semantic. It's also smart, because there's a lot of hidden features inside a graph, so you can apply all kinds of algorithms to get extra knowledge out of it once you have everything connected. And it's alive because it can change whenever you have new entities that you want to add to the graph. There's no problem. It doesn't have a schema or so, like a relational database. You just add entities and you make relationships with other entities. That shows their properties and the relationships between them. So each domain that you work in, each business has its own domain and its own language. And that language basically defines an ontology. The simplest ontology that you can think of is just a list of words. But more complex ontologies, they have relationships between words. There are synonyms, there are abbreviations, there are greater concepts of words, and so on. So you can describe a whole business domain as an ontology. And that, an ontology itself, is intrinsically also a graph. So it fits the graph model very well. So what we are going to do is to see how we can build such a graph, how we can, from nothing, we have nothing yet, how we can start building a knowledge graph and find out our ontology. We just had a discussion in the break about an ontology and semantic people. There is a lot of effort going on in semantics, and you can build ontologies with all these kind of complex semantic tools, but that is quite complex. It also needs specific people who are experts in ontologies. And what I will show you is just a way simpler way of starting with these things and using a property graph instead of a very expensive tool. We start with some classification. It's a very general case. Most companies, organizations, they have lots of whatever. And all the knowledge that is in there, you can only get it out of it if you start reading it and you start labeling it. So somebody is going to read through all this and is going to put a label. This is about that, that is about that, and that contains this and that, and so on. So you end up with a lot of labels, probably a lot of human work as well. And after a while, say after a year, somebody comes up with, we forgot one label. We have to go through it again because the purple ones, we forgot them and they are now so important. You don't want to do that. That's the typical thing that humans don't want to do. So you want to have a machine doing that. So let's build a robot trying to classify all the information that you have, all unstructured or structured information that you have somewhere in databases, old files, it doesn't matter. That's what we are going through. A robot that is going to do this needs to know quite a lot of, needs to be fairly smart. It needs to do some natural language understanding. It needs to be able to extract information, some ontology engineering, named entity recognitions, semantic analysis, topic modeling, and relationship extractions. These are all very important for this robot in order to build the knowledge graph. We're not going through all of these because that would take a very long time, but I'm going just to show you one case that we did for VLAIO, the Flemish agency for innovation and for, how do you say, enterprises? Entrepreneurship, that's the right word, thank you. What they do is actually they provide subsidies to startups and to academic institutions for any kind of research project or any innovation project. And so if you want to do something new, you have a bright idea, and you want to have a startup and you want to make business out of that, you can go to them and ask them for money. You will also need to bring your own money, some of it, but you can get 40% of it, you can get funded by them. So it's sometimes you can get $500,000 if you have a big idea. There are of course a lot of companies who are looking for that type of subsidy. So at VLAIO they get thousands of these applications each year, and when they come in, it's a lot of text. It's 20 pages long. There is a small summary, but the rest of the text, all the detail, is never read by the person who needs to do the first analysis. So when you send them the application, there is a person opens the envelope and he's reading through it, and then he's going to decide it who will be the person that needs to make a decision about this case. So if it's about energy, then we have to give it to the energy expert. If it's about healthcare, we have to give it to the healthcare expert, and so on. And that's a lot of work. They have quite some people reading through these things and making these decisions. So the idea was that's what we are going to automate. So we have lots of documents coming in. These are the applications from the companies. We have some kind of machine, that's the machine there, that is trying to categorize everything and build a taxonomy or eventually an ontology out of it. The way we did that was through machine learning and through topic modeling. This is an example of all the topics that we found, or all the topics. This is the top 30 or so, top 50 of topics. And we see that quite some applications are dealing with energy, quite some other applications are dealing with food, but there are also topics that we find that are not really a topic, like this one. It's companies that says, the big one, the third one from the left. Well, why is that showing up? Of course, the applications are not about companies, they are from companies. So that's part of the business domain of the application itself. It's not really related to the content of the application. So, but these do show up when you do naive topic modeling, of course. The machine knows nothing, so he's just trying to find things that occur frequently. So this is one way that you can find topics, and this is your first step towards an ontology, because from this list of topics you can derive the categories that you want to use as a label for all these applications. One of the issues they have is that sometimes there are new topics showing up. For example, artificial intelligence, that's a topic that is very popular at the moment, so there's a lot of applications about artificial intelligence, but 10 years ago there was basically none. So they didn't have a label yet for it. They didn't have a category and things. Somebody at some point needs to decide. From now on, we are going to use artificial intelligence as a label as well. So how do we go about when we do this with a machine? Well, the machine simply can find artificial intelligence. It will show up in the previous plot, and it will move into more to the front because its occurrence is more often. But still, you have to train your model, your machine learning model, to actually find it in a lot of new applications that you want. And one of the things that we, one of the ideas that we had there was, if we simply teach the machine the Wikipedia page of the topic, it will start recognizing a lot quicker the correct labels. It will label the applications more correctly in a quicker fashion. And it actually worked. The yellow line is if you label everything manually, that's a linear process. The green one is when we do not use Wikipedia pages and we have cold start problems with the machine learning. And you can inject Wikipedia or any other page, of course, that is related to the topic into the system, and then the cold start is a bit shorter. So if you have a new topic, you are much quicker able to label new applications with this topic. We build a small interface for a human because here we see the topic found is energy, and the human simply has to say it's correct or it's not correct. And if it's not correct, we should probably give feedback on what is the correct label. But in this way, we were able to find quite some good results in the data, in the labeling. So once we do all this modeling, we have our taxonomy and ontology. One of the things that you can do with that, a lot of people stop with the categorization and see that as the end point, but you can do a step more, and that is to build a knowledge graph, because everything, all the topics that you find, and all the applications that you find, and all the entities, the named entities that are in the applications, for example, the names of a company, or the names of people involved, or the budgets involved, or whatever. These are all entities that you can put into the graph and create relationships with it. So that's basically what we did. This is just a tiny fraction, of course, of the graph. It's always impressive if you show all these lines, but it's not very useful, of course. So this is a snapshot out of it. You can take subgraphs to actually search for patterns in the system. This shows all the common topics that the applications hold for the universities of Ghent and Antwerp. So in this way, you can probably discover which fields of expertise these universities mainly work in. For the universities, this is very well known. For private companies, this could be very interesting because it gives you a view of what the industry basically is doing and what they are interested in. Here's another example. That's everything that you see applications about bacteria, and so the blue ones are the applications themselves. The bacteria faculties. So in this way, you can actually get some inside knowledge of these systems. And for private companies, I've been trying for a while now to show them that a knowledge graph is actually very interesting for private companies as well, because it gives you a map of your business. If you if you examine all the topics that you have in your business and you relate them with all the entities that you know, and take the data from any data source that you want, bring them together as a knowledge graph, that basically gives you a very good view of your business. which is very good to know. You would really like to know your business. So it's a very general process that we can apply here. We have lots of documents. You can use machine learning techniques to actually start with a simple taxonomy or an ontology. You can really build it from the simple way up. You have a topic learning system. You need that because new topics need to be incorporated into the system. And you can build a graph out of it, which takes you to the knowledge graph. You can also integrate other data, of course. This is a very general picture. So you can put anything in there. And your out-of-the-box site is a good example of where you put out other data in the graph and start relating everything. That's basically also a type of a knowledge graph that gives you insight that you didn't have before. So I think knowledge graphs are very useful for any institution or any company. And that's what I had to say about a knowledge graph. It's fairly simple to start with. Don't be afraid. Questions?
Who creates the relationship, like in year 2005, in year 2000? It's a human that creates this relationship, or we have some view about common repetition, and we have to decide?
Well, that depends. If you start from structured data, if you have multiple structured data sources, then you can probably automate that very easily. But if you have unstructured data, then you either need a human or very good NLP algorithms to figure these kind of things out. If you have unstructured data and you have a lot of it and you use NLP techniques, then you probably need a human to correct things every now and then and to steer it. If you have structured data, then of course you will have Leonardo da Vinci born in. That's in the system, so then it's easy.
Yeah, so this is not unsupervised learning, right? It's not.
The first step is unsupervised. If you have no topics, you simply ask the computer, just tell me all the frequency of words, basically, or certain words. There is some clever, a little bit of smart NLP is behind it. Words like the, and so on, you ignore them. So from that list, you can find your initial set of topics, of your most important words, for example. But then, yes, you need a person that actually is doing the main categories, labels the found clusters, and maybe draws the relationship that this is a synonym of that, or this belongs to that, as a sub class of that. That's what a human initially will have to do. But then that knowledge you can feed back into the system, and if in the future your system will find new things that are tightly related to the existing things, which, and then it certainly becomes supervised learning. Yeah.
So the liquid that was about automating this.
Well, if you have something new, if you want to label if you want to introduce a new label, like artificial intelligence, the system doesn't know about it yet, so it has to learn. It has to learn that if I find this, that, and that in the document, then it's probably about artificial intelligence. And you have to teach it that way, and you can either do that with supervised learning, where human doing all the labeling. No, you did it wrong. Next time you do it better. But that's time consuming. Yeah, so we basically started, we simply took the artificial intelligence page from Wikipedia, started off with that, put that in the machine as trained data, and then he's able to find the right result more quickly. That's basically the thing that it does. Other questions? If not, then I think we are A little bit late, but not too late. Thank you for coming. Rick is already gone, but we are here for